Welcome back, everyone. In this video, we're going to continue talking about periodic trends, and specifically we're going to look at how the effective nuclear charge affects the ionization energy and the electron affinity of an element. Let's begin by talking about what ionization energy is. Think about it this way. An ion is an element that has a charge. The reason why it has a charge is because it has either gained or lost an electron. Now, ionization is the process of removing an electron. And we already talked about ionization when we talked about the Bohr model, and we said that if we take an electron and we promote it to a high enough energy level to n equals infinity, that process is called ionization. So we're talking about removing an electron from an element. Now, in terms of the mathematical definition, ionization energy requires that the element be in the gas phase. And so we're talking about the energy required to remove an electron from an isolated atom or ion if it's in the gas phase. When it is an ion, then we're talking about having done successive ionizations. So, for example, if we look at magnesium, if we take magnesium as a gas and we remove an electron, it requires 738 kilojoules per mole. If we take then that ion and now remove another electron from it, it requires 1451 kilojoules per mole. And if we take that resulting ion and remove an electron from it, that requires 7,733 kilojoules per mole. So we notice a couple things. Ionization energy is always positive. Therefore, this is an endothermic reaction. And also the ionization energy increases as each successive electron is removed. So for a given element, you remove one electron, it takes a certain amount of energy. You remove another electron, it takes even more, an even larger amount of energy to remove that second electron, and then even more to remove the third, etc. So let's take a look at this in another way. Let's say that we're looking at magnesium again. In our first case, we're removing a single electron. And if we take a look at the electron configuration, because remember, we said that these properties can be explained from the electron configurations and the quantum numbers, we see that for magnesium, we're going from neon 3s2 to neon 3s1. We remove our second electron, then we're going from neon 3s1 to neon. And that requires more energy. Now, why does it require more energy? Well, beforehand, when we had the electron there, these electrons were repelling each other. Because they are no longer repelling each other, then the energy of the whole system is lower. It's more stable. So it requires more energy to pull more and more electrons off. Now, once we remove a third electron, now we're going and removing an electron that at that point is in the new outer shell, what was in the core. These electrons are held much more tightly to the nucleus. Thinking again about Coulomb's law, the distance between the electrons in the second and third shell, or from the nucleus, is smaller. So the n equals 2 electrons are closer to the nucleus, which means they're held more tightly, which means it requires more energy to pull them off. And we see that, in fact, that change in energy is very large compared to the previous change in energies. So we saw a doubling of energy between the first and second electron, and then here this is approximately between 4 and 5 times the amount of energy required from earlier. And again, this is because those the electrons on the outside, our core electrons, are much more easy to remove because they're being shielded greatly. If we were to think about what was the Z effective of these electrons, the Z effective of these outer electrons is going to be the number of protons, which for magnesium is 12, minus the shielding electrons, which initially is 2 plus the 8. So that's going to be a Z effective of 2 for these outer electrons. The inner electrons in that second core, their Z effective would be 12 minus 2. They would have a Z effective of 10. So because they are feeling a much stronger pull to the nucleus, they are held much more tightly, and therefore it's a lot harder to pull them off. We can use this information to be able to identify elements based upon their ionization energy trends. So, for example, we have here a plot of ionization energies, sometimes also referred to as ionization levels, as a function of the number. So we're looking at energy as a function of the number of electrons that we have removed. And what we see here is that we have an increasing electron or ionization energy, and it's somewhat linear, and then we have a very drastic increase after we've removed the 5th electron. So my question for you is, what element would this be? Take a minute to think about it and try this on your own, and then we'll talk. Welcome back. Okay, so how do we think about this? We want to remember that the outer electrons, the valence electrons, are those that are the easiest to remove. And that our core electrons are very hard to remove relative to the valence electrons. So when we take a look at the pattern here, it appears as though there are 5 valence electrons, because 5 of them can be removed rather easily. And so you want to then identify which of those elements has 5 valence electrons. Well, when you look at the electron configurations of each of them, you would see that the only one that has 5 valence electrons is nitrogen. And there's a couple ways you can think about this. Aluminum, if we look at its electron configuration, aluminum is equal to neon, 3s2, 3p1. Lithium is helium, 2s1. Nitrogen is helium, 2s2, 3p3. Helium is just 1s2. And then sulfur is, make sure I'm telling you the right one here, neon, 3s2, 3p4. Okay? Remember that the valence electrons are those in the outermost shell. Oh, and this should be 2. No, excuse me. Nitrogen is, yes, 2s2, 2p3. There we go. That is correct. So we have 3 valence electron. The number, if we were to look at the number of valence electrons, aluminum has 3, lithium has 1, nitrogen has 5, helium has 2, sulfur has 6. Therefore, our answer is nitrogen. So, how does ionization energy depend on the periodic table? What properties do we see? This is a plot of ionization energy as a function of the number of protons. And as we go down a group, what do we see? Remember, going down a group is the same thing as a family, so we're looking at elements in the same family here. We see that as we go down a group, that the ionization energy decreases. Now, why might that be? Remember that as we go down a group, we're increasing the number of shells. So if we have our nucleus here with its protons and the electrons, as we increase the number of shells, those outer electrons are farther away from the nucleus. Because they're farther away from the nucleus, They have a larger distance between them and the nucleus, and therefore there is a lower attraction between them and the nucleus. So they're easier to pull off. What about going across a period? What do we see here? Well, going across a period, we can say, let's go from sodium to argon. We see that generally speaking, it increases. However, there are exceptions. Notice where those exceptions are occurring. If you were to take a look at which elements these are, so we have lithium. After lithium, we have beryllium. And then we have boron, carbon, nitrogen, oxygen. Let's see. Lithium, beryllium, boron, carbon, nitrogen, oxygen. Fluorine appears to be missing here. Should be up there. What we see is that when we start a new subshell, this is the start here of a new subshell. This would be the 2p subshell, or the 3p subshell, or the 4p subshell. Those electrons are easier to remove, and that's because there is some slight shielding. Remember when we looked at the radial distribution, we saw that this was our p orbital and this was our s orbital, that the s orbitals slightly shield the p orbitals. Therefore, that makes those p orbitals slightly higher in energy. Therefore, they are easier to remove. This dip down here, or rather, this is actually an increase of stability. I've got these labeled wrong here. This should be nitrogen. Okay, no, that was right. Nitrogen, oxygen, fluorine. So nitrogen is more stable. When we look at its electron configuration, we see that nitrogen has helium, 2s2, 2p3, whereas carbon is helium, 2s2, 2p2. Because we have filled out we have a half-filled subshell, that is more stable than otherwise. That it's because of an increase of symmetry of the electron distribution. Because they are distributed more equally across the element, then that causes an increase of stability. So that's the rise for those exceptions. Now, again, when we think just about what is the trend going across a period, why does it increase? Again, there's a higher effective nuclear charge as we go across a period, and therefore it's harder to remove those electrons. And those are shown here on this plot. We can see that there is a general increase as we go across a period. Again, that's due to the increase of the Z effective, the effective nuclear charge. The last property we want to talk about here is the electron affinity. Electron affinity is the energy that's involved in when we take an element in the gas phase and it gains an electron. So in a way, this is the opposite process for ionization energy, or the ionization process. Ionization is where we take a gas phase element, we remove the electron. In this case, we're adding the electron onto it. Most elements are only able to do this once. However, there are some in the non-metal region where they can gain 2 or even 3 electrons. And there are some important things to note here. One is that certain elements give off a lot of energy when they accept an electron. And for the most part, those elements are our halogens, or the main group 6. These elements prefer to gain electrons. It makes them much more stable. Electron affinity is sometimes exothermic, and sometimes endothermic. Here on this, it is not, there's no values that indicate when it's endothermic. Other things that are important to note for electron affinity is that the noble gases do not want to gain electrons. Also notice that for this period, these elements, zinc, cadmium, and mercury, these do not want to gain electrons, because that would put them, give them a configuration that is higher energy. These are very stable elements. And you'll also notice some things, that the elements which have a completed subshell, these have an S2 and NS2 configuration where they have a completed S subshell. So these are more stable. Okay, this has a completed ND and an ND subshell. So there's 10 electrons in the D subshell. Those are stable. This has a half completed subshell. And so those are more stable than their counterparts. And so we can understand a little bit of the rationale behind it. We can also see that, generally speaking, as we go from left to right, that the absolute value of the electron affinity tends to increase as we go from left to right. So they tend to get larger as we go to the right, and but they tend to get smaller. The absolute value of the electron affinity tends to get smaller as we go from top to bottom. So let's summarize what we've seen so far about the periodic table. Z effective, it increases as we go from left to right, and it increases a significant portion that way, but it decreases and it increases to a small extent as we go from top to bottom. And in all cases, these arrows are indicating an increase. The atomic radius, it increases as we go from top to bottom because we're increasing that's as a function of the n value. And it decreases as we go from left to right, and that's a function of our effective nuclear charge. Higher nuclear charge means the electrons are held more tightly. Ionization energy. Ionization energy increases as we go from left to right, and increases as we go from bottom to top of the periodic table. The reason for this, again, is because as we go from left to right, the effective nuclear charge is increasing, and the same for here. The effective nuclear charge is increasing. The elements are also smaller. They're held, the electrons are held more tightly, therefore it's harder to remove them. And then finally, again, looking at the absolute value of electron affinity, it tends to increase as we go from left to right and from bottom to top. Okay, that is it for this video. Thanks for watching.